Hi Bobcats! In this video we're going to pick up another piece of the mole conversion puzzle, and that is to understand what representative particles are. And we also need to be able to identify for any given substance what its particular representative particle is. So the definition of a representative particle is the smallest piece of a substance that still has the chemical composition of that substance. For instance, if you can imagine taking an element like aluminum, maybe a piece of aluminum foil, and breaking it down into smaller and smaller pieces. You can try ripping and tearing it as much as you can, but then imagine getting even smaller than that, like you've got some sort of a micro machine that keeps breaking it apart tinier and tinier. The absolute tiniest thing that you could have that still would be aluminum would be a single atom of aluminum. Aluminum is an element. As we break an element down, the smallest piece that still is that element is an atom. So that works for elements like aluminum, but different types of matter, like some of the other elements and various compounds, have different types of representative particles. As we start breaking them down, it's something bigger than an atom. It'll be some collection of atoms that's the smallest piece that still is that particular substance. So let's look at what some of those things are. If we're talking most elements like aluminum, iron, etc., the representative particle is going to be just a single atom. But we had a collection of elements that we have to write a subscript of 2 on to represent how they actually exist. So for instance, one of those was oxygen, which is illustrated here. Those 2 red spheres are trying to show an O2 molecule. And that O2 molecule is 2 atoms of oxygen stuck together, and as you are breathing, it is O2 that you are breathing in for your body to use. So there were 7 elements that do that. I refer to those as the Brinkelhoffs. It's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So these Brinkelhoffs are going to have molecules as their representative particle, whereas most of the elements are going to have just a plain atom as their representative particle. We also have covalent compounds, which consist of a nonmetal plus a nonmetal, and those covalent compounds have molecules as their representative particle. So they form these closed units. Once you connect, say in this case, this molecule is carbon dioxide, the black atom is carbon, the 2 red ones are oxygens. So when you connect 1 carbon with 2 oxygens in this manner, you get a molecule, and that's a closed unit. So that is the smallest thing that still is carbon dioxide. So a molecule is the representative particle for covalently bonded compounds. With ionic compounds, that'll be a metal plus a nonmetal, or you have a polyatomic ion present. With ionic compounds, the smallest piece that still represents that substance is what we call a formula unit. So for instance, this substance is a representation of sodium chloride. So the representative particle would be 1 sodium and 1 chloride, which I'm attempting to circle down here in the bottom left corner. So if you have just a single sodium and a single chloride ion put together, we call that the formula unit. That is just literally the atoms that are listed in the formula. That's the representative particle for an ionic compound. When it comes to ions, whether they're monatomic ions like chloride, oxide, consisting of just 1 atom of a single element, or whether they're polyatomic ions like cyanide, shown here, or sulfate or nitrate, acetate. In either case, monatomic or polyatomic ions, our representative particle is going to be the ion itself. So an ion for ionic particles, formula units for ionic compounds that have both a cation and an anion stuck together, a molecule for covalent compounds, and a molecule for the Brinkelhoff elements, And then just an atom is the representative particle for most elements. All right, so let's give this a try. Let's see if we can apply this now. For each of these substances, we've got to figure out which category it fits into. Is it an element? Is it a Brinkelhoff element? Is it covalent? Is it ionic? Is it just plain an ion? And so to do that, I try to think about what elements make it up. Water is H2O. That's going to be a nonmetal plus a nonmetal. And so that's going to be covalent. And the representative particle for a covalent substance is a molecule. For butane, that's an alkane. The formula for butane is C4, right? The but prefix tells us 4 carbons. And then to get the number of hydrogens, we double that and add 2 more. So that would be 2 times 4 is 8, plus 2 more is 10. If we're looking at the elements here, that's a nonmetal plus a nonmetal, so it's going to be covalently bonded, and so that's going to be a molecule as well. In fact, alkanes are a special case of covalently bonded compounds. So the term covalent is a much broader category. Alkanes is completely contained within that category. It is covalent as well, but it gets its own special rules, its own special set of rules for naming. Then we've got potassium phosphate. Okay, so potassium is K and phosphate is PO4 3-. So that 3- charge is an indication, oh yeah, this guy's going to be ionic. We've got to deal with the charges. We would crisscross the charges down as subscripts, so we would end up with a 1 on the phosphate and a 3 on the potassium. So cleaning that up, we've got K3PO4 being an ionic compound. The representative particle for an ionic compound is a formula unit. And there we go, formula unit for this one. Phosphate by itself, on the other hand, is PO4 with 3 negative charges. That's an ion. It's a polyatomic ion, so the representative particle for that is just an ion. Oxide is also an ion. That IDE ending tells us it's oxygen with a -2 charge, not just neutral oxygen. So the representative particle for this one as well is an ion. And I left off from this list one type of substance and one type of representative particle. So let's talk gold. Gold is an element. Its symbol is AU. And for all of the elements that are not Brinkelhoff elements, the representative particle is an atom. And so just to compare and contrast, let's also do just plain old oxygen. Do that down here. Plain old oxygen has the formula O2, so it will not be just an atom, it will be a molecule. That's one of the Brinkelhoffs, and all of the Brinkelhoff elements have a molecule for their representative particle.